privilege to introduce Katja Hofmann to you. We've been hoping for a long time that she could come and join us at the Indaba. Katja, we are so happy that you're here. Actually, really privileged. I'm very happy. So Katja runs a group in Microsoft Research in Cambridge, and she's also the project lead for a project called Project Malmo, which is an agent-based environment that she'll tell you about that runs in Minecraft. She started her career doing reinforcement learning of a different sort. So all of you who use search engines on your phones or on your laptops would know that search engines are optimized over time to give you better and better results. So Katja's career started as someone who optimized search engines, where the search engine is your agent, and all of you are the world in which this agent operates, really big data scale. And now she's operating in another environment, which is a Minecraft environment. I want to say a few other words. We co-authored a paper a few years ago. And I spoke last night about the value of not just co-authorship, but the long-term friendships that result from that, the suffering that you go through when you work together on a project. And this has been a really nice result of working together on something. Katja also works on causality. You can talk to her later about that as well. So without any further ado, Katja, welcome to South Africa. Thank you for being with us.
Thank you. Thank you, Ulrich, and thank you so much to the organizers for giving me the opportunity to speak to you here today. It's been an incredible event for me so far. I've been really inspired and humbled through the discussions with you to hear your stories, learn about your research, and I look forward to many more discussions over the rest of the week. I'm also really excited to be able to share with you some of my love for reinforcement learning and the reasons for why I think it's such an incredible, exciting area in machine learning. Before that, just a few words about myself. On this slide, you can see two environments in which I work. One, the physical, real-world environment. This is the building where the Microsoft Research Lab in Cambridge is based, where I spend most days when I work. And also my virtual work environment, the world of Minecraft. I share this environment with people on my team, my small research team in Cambridge, with which we work on especially trying to tackle multi-agent reinforcement learning in complex environments. And I share this environment with many people worldwide, thousands of enthusiasts, researchers, and students who are using that environment to learn and to do research. With that, I want to start giving you some sense of what reinforcement learning is about. And I know some in the audience do active research in reinforcement learning, while others maybe have heard the word but have no really good association about what that is. So I want to make sure that we start from a good common foundation. And I thought I'd start with a problem that you might have gone through over the past couple of days. For those of you who are in Stellenbosch for the first time this week, it'll be easy to remember the first time you went to the cafeteria, so you won't have to think very far back to think about the kinds of decisions that you might have made. For those who have been in Stellenbosch for a long time, I apologize. You may have to think a little bit further back, but I'm sure some of you might be able to remember your first day here at the university. Now, reinforcement learning is all about decision-making under uncertainty, and it provides a principled framework for modeling how agents, be that natural agents like humans and animals, or be that artificial agents like AI agents or L agents, can reason and make decisions in uncertain environments. Now, the first day you entered the cafeteria, you maybe didn't know what kind of foods every one of those food stalls offered, what it would taste like, what the waiting time might be. So I'm kind of curious to get a sense from you what kinds of information you used to make the decision on where to eat. Let's say, who used the name of the restaurant or food stall? Anyone? The name? Who looked at the kinds of dishes they offered? All right. Who couldn't be bothered and just followed their friend? Anything else? Is there anything else that you kind of considered? Yeah? The length of the queue? Anything else? Yeah? Say again, the colors, so the kind of decoration? Awesome. Anything else? You don't have to raise your hand, just shout. The price. Oh, fantastic. Brilliant. All right. All of those are really interesting kind of features that describe what you can perceive about the state of the world. And you can use those features to make a decision, even when it's not quite certain what the outcome of that decision will be. Now, a quick additional check. Who was satisfied with their choice of food on the first day? Roughly half and half. Who picked a different stall the next day? Oh, wow. Interesting. There's some interesting lessons there about exploration. So how do you know whether you've made an optimal decision, and how do you know whether you should explore alternative choices to see whether maybe you could have gotten a better deal somewhere else? So if you work in reinforcement learning, you start realizing that a lot of real-world decisions can be very much thought of from the perspective, from the point of view of reinforcement learning. And I hope with this example you get a first sense of what that could be like and the kinds of considerations you might want to make, model, and consider when you start working in reinforcement learning, or maybe want to model a problem as a reinforcement learning problem. So to briefly summarize, kind of if you take a first stab at what actually is reinforcement learning, there are two ways in which I like to think about it. First of all, it's a discipline. It's a discipline of science and engineering, where we consider how to make decisions and learn in uncertain environments. So one example of that we have just seen. It's also a type of machine learning that models learning from experience in a very wide range of applications. And this is one of the things that really fascinates me about reinforcement learning, that it has these concepts and ideas that apply to a huge variety of different problems. And because it's such general purpose technique, it can potentially solve a huge number of real-world problems that we try to tackle, that we try to deal with. In that generality, it's very much like other types of machine learning. So for example, in supervised learning, when you start learning about classification, in many ways it doesn't matter what kind of problem you're tackling. What matters is that you understand how to formalize the problem as a supervised learning problem, how to create a data set, and how to process that data so that you can actually learn something from that data. And reinforcement learning is very much the same. So in terms of the agenda today, I want to first dive into a few more case studies, which will also hopefully give you a sense of where the discipline of reinforcement learning kind of came from, the kinds of influences that affected it, and where some of those ideas what motivations, what inspired early researchers in reinforcement learning. We'll then take a step back and formalize reinforcement learning a little bit more so that we can talk about this wide range of problems that can be addressed using RL in a single kind of formal language. And then we will start looking at two types of reinforcement learning approaches. First will be policy gradient approaches, and the second one will be based on temporal difference learning. In between, we'll have just a very short break where you'll get a chance to kind of ask more questions, discuss with your neighbors, so that there's going to be a short mental break halfway through. And finally, we'll also look at some challenges and next steps. All right, ready? Awesome. So let's look at case studies and a little bit of history. As I already mentioned, what fascinates me about RL is that it can model so many different phenomena and so many different decision-making and learning problems in the real world. And this slide illustrates three of the kind of disciplines or areas that people thought about when they maybe unintentionally or maybe unknowingly came up with some of the foundations of reinforcement learning that we still build on today. I want to go through these in a little more detail, but they are optimal control, animal learning, as well as research in learning to play games. So let's start with optimal control. Optimal control problems are a type of problems that inspired much of the early research in reinforcement learning. Although it wasn't called reinforcement learning at the time, It was typically called optimal control. And eventually someone called Bellman came up with some of the key concepts in kind of solving optimal control problem, and he called that dynamic programming. And we'll see some of those concepts later on in the talk. But I want to give you some kind of flavor of what kinds of optimal control problems people were thinking about. Here's a picture of a hydroponic power plant, which some of you may know. Who knows what that is? Yeah? I saw some. Yeah? Right, yeah. So it creates energy from a reservoir, exactly. This is actually a power plant that is in South Africa. I'm not from here. I'm here for the first time, but I looked up kind of big hydroponic power plants in South Africa, and this one apparently is at Jarib Dam. Does that mean anything? Yeah? Yeah, you know it? Okay. Cool. Awesome. So now, the optimal control problem that I want to lay out is that, let's say you operate 2 power plants. One uses kind of traditional fossil fuel, and the price of producing energy from that is stable. But obviously, you might want to minimize using fossil fuel as much as possible. So you only want to use it whenever it's strictly necessary to kind of cut down on carbon emissions, for example. At the same time, you have this hydroponic power plant, and there, whether it's worth using that for power generation depends on the water level in the reservoir, and it depends on the future. It depends on whether it's going to rain or not. And so this is a very kind of simple example, not simple to work out, but it's an example that kind of captures a key essence of what people thought about when they thought about optimal control problems. And that is the nature of these problems in that they have multiple stages of decisions that affect the future. If I make a decision to produce a lot of power using the reservoir water today, that will lower the reservoir levels, and that will influence what I can do tomorrow. And that is exactly the type of decision-making that was captured in those early models. Looking that up, the type of modeling actually had quite a lot of influence on how people thought about energy generation problems. And here's just one example of a study in Colombia, actually, where they used kind of a very simple decision tree model to work out whether they should be using reservoirs at any point in time, and how they could model future inflows into the reservoir, and whether what kinds of consequences their actions would have in the future. Now, this is just one type of optimal control problem, one that has high potential impact in these kind of situations. But the same kind of modeling, the same kind of view of problems can be applied in a wide variety of settings. So people thought about, for example, investment decisions. Should you save or should you invest? Or should I study for a test or go for a dinner, depending on how close I am to the exams? There might be different kinds of decisions that I should make. So what I want to emphasize here is that the key component of this is that there are multiple stages of decisions where you get to the stage of the world whenever you make the next decision depends on all the decisions that you made previously. A second area that was very influential on reinforcement learning is this area of understanding how to play games. And a very early example of that was what's called Samuel's checkers player. I'm kind of curious, who has heard about Samuel's checkers player? Quite a few, fantastic. Everyone else, who knows the game checkers? That's a lot. Who doesn't know checkers? There's a few. Okay, checkers is, as you see here, this board game where you have black and white stones. You can move them kind of one block at a time, and you can win one of these. So, for example, if it's white's turn and they jump over black, then they get to take black stone. And the way you win is by taking your opponent's stones. So that's checkers in just one sentence. This was very early work in gameplay, and what's fascinating here is both the kinds of constraints that Samuel had to work with, but also how early he came up with some of the ideas that are still affecting or still influencing how people model these kinds of decisions or these kinds of problems today. One aspect of this that I was fascinated by was how he decided to represent the kind of state of the board within the computer's memory. And what's kind of fascinating here is that he had to deal with very limited amount of resources, both in terms of memory and in terms of compute. So he came up with compression mechanisms that allowed him to express the current state of the board with as little memory as possible. He also came up with ideas about representing the value of a position based on what kinds of positions they might lead to in the future, which is also something that is still used a lot today. And he also looked at this idea of backup, that once I've reached a node, once I've reached a state, then I can look backwards at what steps I took to get there, and I can propagate information about where I ended up along the paths in this tree. He came up with other ideas that might be familiar to you if you work in this area. One idea is self-play. So he developed this system and had this idea to play it against itself so that it could get better and better by generating a lot of idea by playing against itself. And eventually the system actually got good enough to reach good amateur level, which is very impressive given the resources that he had available in the 50s. And eventually the system was able to beat its own creator. So that was a very early success in AI there. A third area that was very influential, and that where kind of people have gone back and forth between using it as an inspiration, but also to use reinforcement learning to model some of the process that might actually happen in animal and human brains. This is work from Peter Dion's group, which is a group in London that has been incredibly influential, both in reinforcement learning and in neuroscience. And the specific paper that I want to mention here, they looked at to what degree some of the ideas, some of the models developed in reinforcement learning might actually be predictive of some of the things that happen in animal brains. And in this particular study, they used data that was collected from rhesus monkeys. I want to spend a few minutes to kind of walk you through this one graphic that they have in this paper, because I think it's quite fascinating, and it shows on a very nice level to me the connection between the models we look at in reinforcement learning and some of the things that might actually happen on the neurobiological level. So what we have here at the top is a graph that shows the data from many different individual monkeys. So you see one row here per monkey. And they took measurement, a measurement of whether certain dopamine neurons were firing in a certain state. And so you see here that there's a lot of kind of random noise, no clear pattern. Now, the first thing they did was that they presented the monkeys with a reward. So that's, for example, some sweet food that is appealing. And so the first time when they presented the monkey with this reward, they could see the dopamine neurons started firing more than they usually would. So they kind of inferred from this that there was some kind of neurobiological reaction to the reward that was presented here. Now, in the next row, you can see that the monkeys were trained to expect a reward after a certain stimulus is given. Now, stimuli in these kinds of experiments can mean a certain sound or some kind of visual kind of stimulus. But so in this case here, they presented a stimulus, and whenever they presented the stimulus, they then presented a reward afterwards. So there would be the sound, and then there would be some sweet food, for example. And now what they found after the monkeys were trained, they actually saw the kind of spike in dopamine after the stimulus is presented, but no longer when the reward is presented. So the monkeys had gotten adapted to the fact that whenever there was a stimulus, there was a reward. And the only thing that was unexpected now was the kind of onset of the stimulus. Once the stimulus happened, the reward was not unexpected anymore, so they didn't see the firing in the dopamine neurons anymore. Finally, in the third condition here, they presented the stimulus and get the kind of response from the dopamine neurons, but then they did not present a reward. And this is something that's quite fascinating here, that then once the reward was missing, there was this kind of decrease in the firing rate of these dopamine neurons. So what they concluded from this is that this dopamine neuron firing can be interpreted as the brain providing some feedback on whether what was expected actually happened. And depending on whether that expected outcome occurred or not, they would encode information about an error signal. And that error signal is something that is called a temporal difference error, which is one of the models that are used in reinforcement learning. So there's this really fascinating connection between how we can model artificial agents learning in complex environments, and it can also explain maybe some phenomena of how humans and animals may learn in the real world. So I hope I've given you kind of a brief overview of why reinforcement learning is such an exciting area, and the kind of broad variety of problems that people thought about initially when they started working in this area. If you want to read more about specifically applications of reinforcement learning, two of the resources that I find fascinating are by someone called White, who looked at kind of creating inventories of applications of Markov decision processes, which is a way to describe reinforcement learning problems. And he did two inventories of those, both in the 80s, and they include a huge number of control problems, like the energy generation problem that I described earlier. So it's really fun and interesting to kind of see what problems people have used to motivate this kind of research very early on. If you're interested in the connection to neuroscience, here's a more recent kind of overview where the authors looked at a wide variety of neurobiological phenomena and the way to which they may or may not be explainable by some of the models that have been developed in reinforcement learning. Again, fascinating read. Finally, the resource here at the bottom is the holy book of reinforcement learning. It's Sutton and Bartow, Reinforcement Learning and Introduction. And everyone I know who works in reinforcement learning has at some point read this book or is about to read this book. So very highly recommended. It has a wealth of information on this area. And the best part of it is that the authors put a draft of this book online, so it's available for free online. So there's no excuse not to take a look and read this. All right. Before we get into the next session on formalizing reinforcement learning, I was curious just if there are any immediate questions that you would like to ask before we move on. Looks like everyone's good so far. All right, let's move on. All right, in the next section, we'll start looking at formalizing RL. So in the previous couple of slides, I tried to give a kind of intuitive picture of what reinforcement learning is and what kinds of phenomena can be modeled using reinforcement learning. Now, it's important to also formalize this a little bit more. And the reason why it's really important is that we need a common language to express all those very diverse, very different problems that can be addressed from a reinforcement learning point of view. And only that common language, that common formalization, allows us to then develop approaches that are general and that can be applied to that wide variety of problems. If you've heard any talk about reinforcement learning before, then you have seen this kind of picture. It's obligatory in the reinforcement learning talk. And it very briefly encapsulates the kind of interaction that an agent has in an environment when the agent is modeled as a reinforcement learning learner. So the interaction between agent and environment proceeds in time steps, and I want to illustrate some of those time steps on the coming slides. So the key distinction between reinforcement learning and other types of machine learning approaches is that the agent is thought of as being embodied in some environment in the world, and that it continuously interacts with this world, gets more information about the world, and has to learn from that in order to take good decisions. Now let's look at the time steps in which this takes place. At the start, the agent may see some information about the world, and we call that it observes a state, in this case as 0, because the interaction just started at time step 0, which comes from some kind of potential set of states. If we think back about the cafeteria example, then the kind of, if you think about the first time you enter that area, you may perceive all the information that we mentioned, for example, the price, the length of the queue, the types of food that are offered, etc. So these are all kind of features that describe the state of the world at that point in time. Next, the agent generates some action, takes an action, and we call that again A0, which is drawn from some set of potential actions that the agent can take. In the example here, the agent might pick one of the food stalls, one of the restaurants that is available. Now, at the next time step, the agent observes two things. One, we get the next state. So, for example, in the restaurant example, the agent is now full and has either enjoyed or not enjoyed the meal. But so whether the agent has enjoyed the meal is something that we call reward. And this can be thought of as a specific observation from the environment that gives the agent some information, some kind of feedback that is useful for learning. So now, based on the information that the agent has received, it can update, for example, its behavior or its model of the world to incorporate, well, once I took this particular action in this particular state, I observed this reward, and the reward can be positive, so that might mean that the agent wants to learn to take these kinds of actions more often, or it could be negative, so the agent could learn, okay, this is something that I should avoid in the future. Right? And this kind of interactive loop keeps going on and on and on. And we say that within this kind of interactive loop, there are two kind of components, two kinds of functions that drive this behavior. On the one side, we have the agent, which acts with a policy, which we typically call pi. So pi is a probability distribution over actions given a state. And on the other side, we have an environment which develops according to a function that is called transition dynamics, where these transition dynamics again encode a probability distribution where the probability of the next state that we observe depends on the previous state and the action that was taken by the agent. Finally, we have some kind of reward function which just tells us what kinds of rewards are emitted given a state and a given action. And now this interactive loop, this model, is what reinforcement learning researchers describe as a Markov decision process. In a paper on reinforcement learning, you typically don't see that kind of interactive picture, but people just write, we assume that the agent and environment interact according to a Markov decision process, which is characterized by a state space S, an action space A, some transition matrix P, and reward function R. There's also typically some kind of discount factor gamma, and I'll explain what it means later. But so a key assumption that this Markov decision makes is that the dynamics that I've just described adhere to what is called the Markov property. So as I shown on the previous slide, as we went through the cycle, the dynamics of the environment only depended on the previous state and the previous action. So that means that we can make a simplifying assumption. When we want to understand, when we want to model how the agent could learn to act in the environment, in principle, if we didn't make this Markov assumption, then the agent might have to kind of take into account the entire history, everything that is ever observed about the world. Now, with this Markov assumption, we can put ourselves in a much, much simpler setting. We can say that we assume that the next state that we observe only depends on the state we were in before, as well as the action that was taken. And that means that now the action that the agent takes next only needs to depend on the previous state of the world. So it's very much a simplifying assumption, which enables some of the more tractable approaches to reinforcement learning. All right, finally, I promised I'll tell you what this discount factor is about. The discount factor is important when we talk about the goal that the agent should be striving to optimize. There are many different kinds of formulations, different goals that could be formalized, but the one that is the most common is that we want to develop agents that take actions that maximize a discounted cumulative return. And what that means is that if we consider the entire sequence of time steps, starting from some point 0 all the way up to infinity, we want to maximize the sum of the rewards that are observed by the agent, discounted by a discount factor gamma to the t, which means that rewards in the near future are weighted higher than rewards that are further out. And another way to interpret this is that the discount factor gamma gives us some probability that the interaction with the environment might end at any one point in time. If the environment or if the interaction, if the game could stop at any one time, then we should optimize for rewards that come sooner rather than those that come later on, unless there is a way for us to kind of interact in such a way that we get a very, very high reward at some point in the future. So that's what's encoded by this discount factor. Now, moving on from this kind of more formal description of the reinforcement learning setting, I want to take some time to go through examples of how the states, actions, and rewards in a reinforcement learning problems could be chosen or designed. And we'll get back to the more formal description when we get to the reinforcement learning approaches themselves. So first, let's look at some examples. Now, one thing to notice that when people do research in reinforcement learning, very often they assume that the choice of states or actions and rewards is something that is provided externally. It's something that someone pulls out of a hat. And this is a little satisfying because, to me, the key point to when you want to apply reinforcement learning in a real-world scenario is that you need to understand how to formalize a problem, how to formulate it as a reinforcement learning problem. And the key design choices there are how to actually encode the state of the world to ensure, for example, that the Markov property holds and that the agent is able to learn to make decisions based on just the most recent state observation. How do you ensure that the actions that it's given allow it to actually optimally solve the problem? And how do you pick a reward structure that encourages it to actually learn the behavior that you desire? So let's take a few moments to take a look at what this could mean. So let's look back at the example of the hydroelectric power control problem that I described earlier. There we could make very different choices about how we encode the state of the world, the state of the environment, to allow an agent to learn to take decisions. One choice would be to use discrete states where we just say, this is low, or the level of water in the reservoir is low, or it is high. So it's a very small state space. It just has two states. Or we could take discretization, which is coarse, but provides a little more kind of granularity. So for example, we could say the water level in the reservoir is between 0 and 10%, 10 to 20%, or it's between 90% and full. Or we could encode the state of the world as continuous states. So we could say the current water level in the reservoir is 53 meters. Now, between these three choices, I'm curious, what are your intuitions of what might be a good choice? Do people have any thoughts on that? Mm-hmm. 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 Right, so the answer here. Mm-hmm. Okay, so the answer here is, let me see if I rephrase this correctly, would be that A could be a very good choice. If we compare this to the checkers example, then this would be a representation which is very small. It requires very few resources. It might be quick to learn. Is that in line with what you said? Mm-hmm. Are there any other thoughts? Yeah? Mm-hmm. Okay, so there the answer is to look at continuous states, because we might want to actually learn a precise threshold of when we want to start generating power from the reservoir versus not. Okay, so this allows us to kind of learn on this more granular level. Mm-hmm. Any other thoughts? Yeah? That's a very diplomatic response, and it's a very good one, I must say. So the response was that it depends. And it depends on things like what kind of solution you're looking for, what kinds of resources we have available, what kind of expert knowledge we might have. So for example, if we have very little knowledge and a lot of resources, then learning something fine-grained like a threshold might be a good idea. If we have to very quickly learn a reasonable decision, something coarse, like just 2 levels of discretization, might be right. And this is a really good realization that there is no single hard and true choice that could tell you that this is definitely the right choice for how to formalize those states. It very much depends on the constraints, on your resources, the time you have available for solving the problem, etc. So on the next slide here, I just summarized kind of some of the important choices and considerations that need to be made. The one thing I want you to take away from this discussion is that if you want to apply reinforcement learning to any problem, you need to really think hard about how to represent state observations. And it's a really important modeling choice that will have very important implications for the kinds of solutions that can be learned. And there's trade-offs to consider. So for example, let's start with data efficiency. So if you have a less granular, if you have a very kind of large state space or a very complex state space, then you may need a lot of data to actually learn a solution. Whereas at the same time, if you have a lot of data, then given that more flexible representation, you might be able to learn solutions that are better, that are more optimal than the ones that you could learn with a coarser representation and fewer data samples. You may also want to consider whether the Markov property is satisfied. So do you actually have the right information in your state representation, and does it contain all that is necessary, all the information that is relevant to actually solving the problem? So thank you all for those contributions. Based on kind of the kind of understanding of how to model the state space, there are 2 papers, 2 types of works that I want to highlight here, which really changed the way people thought about what reinforcement learning can do. And the first one there is the work by DeepMind by Andrew Neer et al. On learning to play Atari games. And the reason that this is so important and why it cannot be overstated how important this was that it was a lesson in generality. So in this paper, the authors showed that with a single algorithm, with a single model, and a single choice of hyperparameters like learning rates, etc., a single reinforcement learning agent, or a single algorithm, was able to learn a wide variety of problems, and in this case, a wide variety of Atari games, 49 different games, which were all challenging games interesting to humans. And it was able to learn those from a very raw form of state observation, just the pixels on the screen. And up to this point in time, I think many people in reinforcement learning didn't believe that was possible. So I really believe this is one of the kind of breakthroughs, and it happened only a few years ago. It's already given rise to such exciting new developments in the field of reinforcement learning. It's essentially the starting point of what we call deep reinforcement learning. So this is something that is really exciting to me. Another study that I find really fascinating is one that was published at the ICML conference this summer in Stockholm. And this is also one that kind of had a really interesting take on how to look at state, how to look at observations, and the kinds of biases that might be used for learning from those state representations. So what the authors here started with was the observation that looking at learning to play Atari games, human players still learn a lot faster than what is currently possible using deep reinforcement learning algorithms. Deep reinforcement learning algorithms are now able to beat human players on a wide range of Atari games at some point, but they still need on the order of millions and millions of samples to actually achieve that performance. Whereas someone, a 10-year-old kid, you put in front of an Atari game, they learn to play it pretty well within a couple of minutes. And there's just this enormous discrepancy. So what the authors here looked at was trying to understand what kinds of biases people might use to quickly learn how to play a game. And they investigated this by systematically removing some of the biases that they thought played a role. So I'm going to walk you through some of those examples. So on this slide here, you see the original game that they used. And if you're familiar with the Atari game Montezuma's Revenge, this should look reasonably familiar. So it's modeled on a game that is notoriously hard for reinforcement learning agents to learn, but something that is reasonably simple for a human player. There's actually a website associated with this, so if you're interested, it's fun, you can try it out for yourself. This is what it looks like when a human plays this game after, I don't know, a couple of minutes of practice. So they're able to progress through the game fairly quickly, go up the ladder, grab the key, move over to the door, bam, level solved. Okay, very easy for humans. Now, the first thing they considered was looking at what is the role of semantics when people learn to play a video game. So on the previous slide, on the original game, we saw that the objects there had very specific kinds of forms and shapes. So you could see, for example, these spikes over here. Okay, that might be danger. There's ladders over here. That might be something where you can go up. So the first kind of test that they did was that they masked the semantics. And you can see an example here. Everything is just colored blocks. And they try to remove the bias that we have that the objects that are on the screen might resemble something that we know from the real world. Now, when we compare humans to reinforcement learning agents typically don't have a lot of information of what objects look like in the real world, so that might be a disadvantage to them. Now, on the next slide, I have a graph of how human and how reinforcement learning agent performance was impacted when playing with the masked similarity condition, or masked semantics condition, and I want you to guess first, who was more affected by masked semantics? Was it the human players? Or was it the reinforcement learning agents? One person is sticking it up for the reinforcement learning agents. Okay. I think you have exactly the right bias there. So if we look at how human players' behavior changed on your right, you can see that the time it took them to complete a level, the number of deaths per attempt, and the kind of wide range of states, so the amount of space that they explored while playing, dramatically went up in the masked semantics condition. Whereas for the deep reinforcement learning agents, there's no change at all. So it kind of gives an interesting insight that essentially when reinforcement learning agents learn to play from a visual representation that we think we're very familiar with, that we know very well, where we know, well, we can really capture what we input into the RL agent's kind of observation space, that the agent still interprets that kind of visual representation in a very different way from how a human would be interpreting it. I have another example here. The next bias that the authors were looking to address was masking identity of objects. So you may be aware that the notion of what an object is kind of hard to characterize. But here they have an approximation for that. So instead of kind of only putting colored blocks or only putting blocks where the obstacles are, where the monsters are, where the keys are, everything is filled up with different colored blocks. So it becomes harder to interpret, well, what is an object and what is not an object. Again, the guess, who was more affected by that particular condition? Humans or RL agents? Few more for the RL agents. It's still the humans that are affected a lot more. Actually, it got even worse than with masked semantics. When humans don't know where the objects are, their performance really, really drops. Whereas for RL agents, they have no notion of objectness whatsoever. So it's a really interesting lesson learned here. Again, humans and machines interpret even the visual observations that we think we know how to interpret in very different ways. And at the same time, there might be lessons learned here for potentially improving performance of reinforcement learning agents. Maybe there's some notion of objectness that we can help them learn, which would improve performance there. So it's a really exciting study. As I mentioned, there is a website where you can play the game under all these conditions. There are some that I haven't shown, including one that actually makes it harder for the reinforcement learning agent to learn. But to figure out which one that is, you'll have to go to the website or to the paper and look that up. Okay, we talked a little bit about the state space and kind of discussed why it's a very important design choice. I'll go over action spaces a little more quickly. Again, the choice of action space is really important to tell what kind of performance can be achieved. And again, we have trade-offs between how quickly the agent can learn. With smaller action spaces, learning may be more quick, but generalization might be harder. Different choices include things like discrete action spaces, for example, turn a system on or off, which button to press, which is the kind of action space used in the Atari games. It could be a continuous action space, for example, how much force to apply, how quickly to accelerate, how fast to move in a certain direction, how quickly to turn. And there is a wide kind of open active research area, which includes learning in complex large action spaces. Some examples here include action spaces that are combinatorial, action spaces that mix discrete and continuous signals, and things that use something as complex as, for example, natural language. Just a very quick pointer, if you are interested in reinforcement learning, maybe doing research in this area, one platform that was just published that allows research in complex action spaces is this environment called Text World, where a team from Microsoft Research opened up text-based text-based computer games for reinforcement learning research. And the aim here is to kind of encourage research in this direction of very complex action spaces up to the level of the complexity of natural human language. The third set of examples and kind of important choice when we look at reinforcement learning problems is this question of rewards. So we very briefly discussed previously that, let's say in the cafeteria example, the agent may observe some signal, positive when it had a good experience, negative when it had a negative experience, and that allows the agent to learn from its experience. Again, in a lot of reinforcement learning kind of papers or textbooks, it's assumed that the reward structure is something that is imposed kind of from the outside world on the agent. But for a practitioner, someone who wants to apply reinforcement learning, it's a key modeling choice. And it can really have a strong impact on whether the agent is able to learn anything at all. Something that people have found over the past few years is that reinforcement learning agents are really good at exploiting aspects of the reward structure that maybe wasn't known to the experimenter. And there's some very, very interesting examples of how what the experimenter was anticipating was not at all what the agent learned. I want to show you one example that was developed by, or that was shown by people at OpenAI. This is a video game where, let me go back one slide. Okay, this is a video game where players have to race this boat around a track. And one natural choice of reward function in a video game is the score that the human player would observe when playing this game. And this is kind of a natural choice which was also used in a lot of the work on Atari games. So OpenAI made available a wide range of video games for experimentation with reinforcement learning agents, and this boat racing game was one of the games that they made available. Now, the very weird behavior that was learned is something that, let me start playing again, is that instead of racing to the goal, the agent actually learned to exploit the reward structure in a much more interesting way. It turns out that there's a very high score when it hits these 3 green barrels that you see here. So all the agent was learning was that it could bump into all the obstacles, cause as much damage as possible, as long as it would hit these green barrels the moment they respawn. It's a very, very effective way to maximize your score. It's not at all a good way of playing the game. So on the topic of rewards, I just want to emphasize that it is a very important modeling choice. there's some really cool and exciting research going on in this area, trying to understand how to set goals for reinforcement learning agents, how to create reward structures that discourage this kind of learning of exploitative behavior, and to learn behavior that is actually in line with what the human, with what the experimenter or the system developer had in mind initially when creating the setup. All right. Just a little bit of further reading on this section. A very good discussion of kind of states, actions, and rewards is again in the Sutton and Bartow book, and here I want to highlight chapter 3 and chapter 9 in particular. All right. Before moving to the next section, looking at how to actually approach reinforcement learning problems, are there any questions that you would like to ask? Yeah, oh. Fantastic question. In a lot of the kind of standard reinforcement learning literature, the simple assumption is that there's a single scalar reward signal, so that it's a single number which can be positive or negative. There's some really interesting work in multi-goal reinforcement learning where there's a more complex reward structure. And that models very well situations where there might be a trade-off, the quality of food versus the length of the queue, where maybe the application developer doesn't know ahead of time how to trade those off. So we might want to develop agents that can actually learn some kind of space that maximizes a Pareto front in terms of these multiple reward signals, where then either the kind of application developer or in some other way we can choose later on what solution we actually want to deploy. Yeah. It's an ongoing line of research, and there's some fascinating work. Oh yeah, it's hard for me to see arms, so if you just scream, that'll work. Yeah, so if you look at kind of theoretical guarantees, there's always an assumption that the reward is bounded within some range, and you need that for the guarantees to actually work out. In practice, especially when you work in reinforcement learning, like deep reinforcement learning with function approximation, there's some considerations about the range of rewards and how easily you can optimize for them. A lot of that is more an art than a science. For example, in the Atari work, people clipped the rewards between -1 and 1. There are similar choices, and a lot of that is really just testing it out on those specific applications. Mm-hmm. Absolutely, absolutely. Fantastic question. So you may know some of the answers I'm suspecting. There's some very exciting recent work that looks at more general forms of reward, as you mentioned. Novelty is a very important one. People look at notions of curiosity. So based on kind of our notions of how animals or humans might explore their environment, driven by situations that maybe they cannot predict, people are looking to formalize that in information theoretic terms to quantify or to learn what is a novel situation. And so there's, again, some fascinating research coming out. The most recent ones are at ICML this year, and I'm sure there will be some really exciting ones at NIPS coming up as well. Yep. Very interesting question. So the question is, are there situations where an agent might get stuck in a plateau or in a certain suboptimal solution? And is there any work on trying to get beyond that plateau and get out of it? There are a lot of different directions that have been studied, actually decades of work. Some of those are related to kind of shaping the reward structure in a particular way. So for example, people have used optimistic initialization, which artificially draws the agent to parts of the state space that haven't been visited. And that can be, again, related to notions of novelty and curiosity. It turns out that that can be very effective, but it could also draw the agent towards areas that are maybe unsafe. There's interesting work from DeepMind on population-based training, so that might alleviate some of the problems. If you have many different copies of the agent that maybe randomly gets different parts of the data, then some of them may perform better than others. And there's interesting work where they look at, well, what are the agents that have performed best so far? Which ones should be continued to train in order to get best performance over that entire population? There's other work on distributed exploration when you have multiple agents. So for example, you can split up the world and kind of assign agents to different parts of the world to explore. Again, this is something that is very effective. Mm-hmm. Let's see. Oh, yep. Mm-hmm. Mm. Yeah, fantastic question. So the question is, how do you deal with delayed rewards when there are a lot of steps required before you can get to the goal and actually see that you've done a good job? And it's fascinating because Samuel, with his checkers player, was actually discussing the same thing. He was like, well, in principle, I should just check and see whether the agent won or lost at the end of the game. But that would involve so many steps that I cannot reasonably work that out within the methods that I have available today. And in the 50s, that wasn't really possible. Today, that is sometimes exactly what people do. The problem is a problem of credit assignment. If you have taken 100 steps and finally got a positive reward, how much did each of the actions you took along the way contribute to the reward that you actually got at the end? And if you have a lot of data, if you're able to maybe generate data cheaply in simulation or in a game environment through self-play, then because we have very effective tools now for optimization, this can actually work. But there are ways to speed that up, and if you have expert knowledge about the structure of the problem, you might provide intermediate rewards. And there's an area called reward shaping, which looks at the kinds of ways in which you might want to provide those additional rewards without actually changing the structure of the optimal solution that you can learn. All right. With, yeah. Mm-hmm. Right, right. Mm-hmm. Right, right. Fascinating question. So the question is, how well does reinforcement actually work in practice in a world that is very dynamic, that can change in unpredictable ways, where we don't really know what is going to happen? Now, the short answer is that reinforcement learning is designed for exactly those situations. And an ideal reinforcement learning agent would take into account its uncertainty about the world and how it's going to develop in the future. So I can take decisions now, even though I don't know what tomorrow is going to be like. And we can model those kinds of decisions using reinforcement learning. In practice, I think there's still a lot of limitations to actually deploying reinforcement learning solutions in the real world. For example, we may not want to have reinforcement learning agents that start randomly exploring how to control our electricity plants. That, might be a little scary. So people are looking at solutions that kind of make reinforcement learning practical in real-world applications. There are specific areas. One area is in contextual bandit problems for example, recommender systems, web search, and things like that, which is an area where there are actually practical solutions that are already available for people to use. There are people looking at safe reinforcement learning. So again, looking at what are the kinds of constraints that we may need to work with when we actually want to deploy these agents that go out into the world, be that virtual or be that the real world, and start to learn. But how can we make sure that this is safe and controllable and that it works and fits with the human kind of shaped environment that we want to deploy those in? Fascinating question, and again, a lot of work that is still open. All right, I want to move on. We are about an hour into the discussion, so I want to make sure that you just get a few minutes to kind of get up, stretch your legs. So I suggest that we stay here because it's really hard to get everyone out and back into the room. But I encourage you to talk to your neighbor, come up with one example of an application where you think reinforcement learning could be a good kind of approach to develop. And we'll continue in just 5 minutes, and I want to hear some example applications that you've come up with. Thanks. Yeah. All right, let's start to continue. All right. So I hope in the discussion with your neighbor, you were able to identify maybe one or two kinds of problems, application areas, where you think reinforcement learning might be a good kind of approach to tackle this problem. In the next kind of part of the lecture, we're going to look at two types of approaches for actually solving reinforcement learning problems. And I invite you to, as we go along, think about how those approaches would look like if you were to apply them to the problems that you have discussed with your neighbor. And after the lecture, I'd be really curious to hear about the problems that you've come up with. So please talk to me afterwards if you think you've come up with a cool application for reinforcement learning. But so let's take a look at the different approaches for addressing these. We're going to look at two approaches that are quite different in flavor. So one of them focuses on really improving the behavior of the agent, whereas the other starts from the point of view of evaluating, measuring the performance of the agent. The first one is called policy gradient approaches, and it starts by developing some intuition of how those types of approaches work. The focus, as I mentioned, is on learning a good behavior policy, and we're going to start by looking at a very small toy problem, which is a simplification of a reinforcement learning, which is called a multi-armed bandit problem. The reason this type of problem is called multi-armed bandit is what you can see on this slide. Back in the ancient days of these early slot machines, there were those so-called one-armed bandits, where, as you can see, there's one arm. You pull the arm, you get a reward, either some money, or you lost the money you put into play. Now, a multi-armed bandit problem is one where you have several of those, which kind of stand for the different action choices, the different decisions that you can make at a point in time. And notice in this particular simplified version of reinforcement learning, there's only a single state. So every time we come in, we see these two machines, we can pull the arm of the right one or the left one. Now, assume we're in a casino where these machines are rigged. One of those actually has a higher payoff than the other. Now, how do we know, how do we play so that we can actually maximize the amount of money that we have, let's say, after playing 50 times? Now, let's look at how we might approach this. As I mentioned, we're going to focus on learning a policy. And because initially we have no idea about which machine is the better one, we just put a uniform probability on each of them. So initially we start with a uniform random policy where we have a 50-50 chance of picking each action. Now we're going to flip a coin. That coin flip, let's say, comes up heads. So we're going to pull this particular machine. And we lose. Now what do? We adjust our policy. We say, well, we got a negative reward, so let me try to do less of this again in the future. In this particular case, you can imagine that maybe we slightly lowered the probability of pulling the arm of that particular machine, and we slightly increased the probability that we pull the other machine. Now, next one, we again flip a biased coin. We randomly pick this particular machine the next time. Yay, jackpot, we win. Now what do? Again, we adjust our policy. We take a small step towards taking the action that actually got us a positive reward. And now let's say we have a 40% chance of drawing the arm on the right and a 60% chance of the other one. Now again, we flip a biased coin, we pull that arm, we get, hey, another win. Maybe this machine isn't so bad after all. And also, this is probably not a very realistic casino, if you've been. But I think you see the intuition. But so to summarize this kind of intuitive level of how policy gradient approaches work, is that you repeat these two steps continuously. You collect some experience using the current policy. That means you sample an action from whatever your probability distribution over actions is. You get the reward associated with that particular action that you took, and then you update your policy so that you're more likely to get positive outcomes in the future. Now, starting from that very intuitive explanation of policy gradient, we need to make two things precise. First of all, what is the particular shape or form of the policy that allows us to do this kind of learning? And secondly, what do we mean when we take a small step in the direction towards better outcomes? And according to the policy gradient method, there are actually very mathematically precise ways that allow us to say, to qualify what exactly we should do, what kind of policy we can use, and how to update that policy as we learn. Now, there are many different ways in which the policy could be parameterized, but a very common form is the one that I'm showing here on the slide, which is called a softmax policy. Now, in this particular kind of notation, just highlighting a few key components here. First of all, as we've already emphasized before, the policy is actually a probability distribution over actions given the current state. So that's indicated over here. Secondly, the policy is parameterized. We're indicating that with the theta here, which is a vector of learnable parameters. And those are the parameters that we update as we learn and improve our policy. Next, a softmax policy is characterized by this particular function here, which encodes action preferences. The action preferences here are formalized in such a way that we're more likely to take actions where there's higher preferences. So you can imagine this h of SA parameterized by theta here, for example, as a linear function that maps the features of the state in action to some kind of scalar preference. And the higher that preference, the more likely we are to actually take that action. Finally, here in the denominator, you can see that this is really just the sum over all actions and all the action preferences. And this is simply used to normalize to ensure that we have a proper probability distribution over actions that is normalized to 1. So this is a very, very common choice for policies in policy gradient settings. And I just mentioned that this is a form that is particularly convenient to work with and to update using policy gradient. Next, now that we have a policy, we need to write down the actual goal, the objective that we want to optimize. In this particular setting here, we want to find the parameters theta that maximize some expected reward. In our case here, this expectation is over all possible states and the distribution over states that we would get if we were to run the current policy for an infinite amount of time in our particular MDP. So this is what's called the stationary state distribution. We're also looking at an expectation over actions. So for all possible actions, what is the probability of taking that action under our current policy? And then we multiply the probability of taking that action by the long-term reward that we expect by taking this action in that particular state. Oops. And what I just said, we have the stationary state distribution under our current policy, we have the actual parameter S policy, and we have the expected return when starting from a state S and taking action A. Now, the challenge given this objective is that we need to find a way to optimize this objective, so update the parameters of the policy theta so that this objective is maximized. A key insight was developed by Richard Sutton and his colleagues in 2000, and it's called the policy gradient theorem. And the policy gradient theorem tells us that we can actually derive the gradient, so we can find the direction of maximal improvement of the objective by just looking at the gradient in the policy parameters. So the key insight here is that the gradients of this objective are independent of the stationary, the gradients in the stationary distribution over states. And this is a great simplification, and it's key to actually allowing us to estimate all the quantities we need to learn the policy from the data that we can interactively observe by interacting with the environment. So what this means is now that when we look at the gradient in our objective, so the direction in which we need to update our policy, we can estimate all relevant terms from the data that we get from interacting with the environment. We can approximate the state distribution using samples collected under pi. So that means we run the policy on our environment for some large number of steps, and we can estimate the probability of being in each state based on those. Or we can just approximate the sum by taking samples from that state distribution. Similarly, we can approximate the expectation here over actions by using samples from our policy pi and re-rating by the probability of taking that action under the policy. So again, this is a principled way to approximating this expectation over actions. And then finally, we need this quantity here, the reward. And again, we can approximate that using the actual sampled return by rolling out the policy in the environment. So now, as you can see, all of those quantities can be approximated just by using the samples, the state actions and rewards we get from interacting with the environment. The final thing that we need to compute is the gradient of the policy. The gradient of the policy of A given S in the policy parameters theta here. Now, very pragmatically, if you actually implement this, in practice, you're going to use your favorite deep learning framework to implement the forward pass through the policy. And then you're going to use that same framework to compute the gradients using AutoDiff. So in practice, as you get started with reinforcement learning and policy gradients, you're unlikely to actually have to compute the gradients yourself. But I just want to mention that the particular form of policy that I introduced earlier, the softmax policy, especially when it uses a linear feature representation, has a particularly simple form where the gradients can be computed easily analytically. This particular form was used, for example, in this paper here by Sutton in 2000, and it was also one that was used in one of the earliest reinforcement learning algorithms, which comes under the simple name reinforce, because it was so fundamental. On this slide here, I have a very short form of this algorithm, which was initially proposed by Williams in '92, and which was analyzed in this paper by Sutton and his colleagues in 2000, which put this on a very systematic foundation where it was understood that we can actually estimate all the relevant quantities from that interaction data with the environment, as I mentioned earlier. Now, the key components that I just want to highlight here are these two steps that we kind of looked at earlier as well. So the reinforced algorithm runs in this interactive loop, where in each episode, the current policy is used to generate some data. So we already saw the form that takes, we get some initial state, we take an action, we get a reward, et cetera, et cetera, et cetera. So we follow pi, we run this on our environment according to the environment dynamics, and we get this interaction history. And now, for all the data that we collected, we want to update our policy to actually move in the direction so that we get better outcomes in the future. So for each step along the trajectory or episode that we collected, we first look at the return, G, which is the sum over time of the rewards that were actually observed. And you can see the discount factor here, which, as we mentioned before, encourages reward or gives higher weights to rewards that are near in the future, near rather than further out in the future. And then secondly, there's an update to the policy parameters theta. And this is really the important step where we take a step in the direction of the gradient of the policy with respect to its parameters theta. So we update the parameters theta by some learning step alpha, which is the learning rate, and this is a hyperparameter of the algorithm, times the discounted reward that we just computed, times the gradient of the policy with respect to those parameters theta. And there, in a few lines, we have a very first algorithm that can be used to effectively address some reinforcement learning problems. And of course, the history of reinforcement learning would be rather short if it addressed all of them, but at least it's a practical algorithm for some set of environments. And I believe in the practical later this afternoon, you'll actually get to play with this algorithm and develop more intuitions on how it works, what its opportunities are, but also some of the challenges. I want to conclude the section which looking at two applications where policy gradient approaches have been used. The first one is a kind of work by Das and colleagues, which was published at ICCV, Computer Vision Conference, last year. And they looked at the problem of learning cooperative visual dialogue agents with reinforcement learning. So this is a really fun and exciting setup where you have a questioner agent which can ask questions to an answerer agent, where the answerer agent has some picture in its mind, and the questioner agent has to figure out which picture the answerer is actually referring to. So, for example, the answerer might start and say there are two zebras walking around their pen at the zoo, and the questioner agent, which cannot see the picture, could ask, are there any people in the shot? No, there aren't, et cetera, et cetera. And at some point, the questioner agent has to figure out which of the images, so for example, this one, the answerer was referring to. Now, the key challenge in this kind of setup, as in many kind of applications that include natural dialogue, is that we cannot optimize dialogue end-to-end. So you cannot find a single forward-backward pass through the questioner and answerer that would allow you to actually optimize all the way through. And that may be possible in artificial settings, but if you look at an application where, let's say, an AI agent has to converse with a human, you can imagine that we cannot backpropagate through the human brain in order to get the right gradients for the questioner. So there's a key limitation there. And now algorithms like reinforce, policy gradient algorithms, have turned out very effective black box optimization techniques that actually allow us to learn in a principled way in settings where there is such a step, where there's a step that where the agent has to make a hard choice, where it has to take an action, and where we cannot propagate through the environment in which that action is taken. That is true in environments or in problems that include dialogue learning like this one here, and it also includes application, for example, in knowledge-based access or database access, where you may want to kind of instruct an agent to go find some information in a knowledge base, but at some point you have to take an action, query the knowledge base, and you cannot backpropagate through that. So reinforce and other approaches of this type are very important black box optimization techniques that to me were quite surprising that they're so powerful in those settings. A second application that I want to highlight is a very, very recent one from OpenAI. This one is in the area of dexterous manipulation. In this approach, the authors did not use vanilla reinforce or vanilla policy gradient. They actually used an advanced implementation that is highly scalable and can process enormous amounts of data, which is called PPO, Proximal Policy Optimization. But there are still roots. The approach is rooted in the same kinds of principles as vanilla policy gradient that we looked at earlier. And I want to just use this as a motivation to kind of, if you're interested in this area, starting from understanding policy gradients, there are very, very exciting approaches that people have proposed recently, including an approach called TRPO, including PPO. So there's a very active research area around policy gradient algorithms, understanding how to improve them further, how to make them, for example, more data efficient, and how to allow them to learn more and more complex kinds of behaviors. So just to briefly show this video again, this is an approach where where a robot has learned to manipulate these kinds of blocks according to the tasks that are shown here. And as you may have heard during the Indaba earlier on, dexterous manipulations is actually one of the hardest tasks in robotics, one of the hardest tasks that is being tackled using reinforcement learning today. Right? So that was a very, very quick introduction to policy gradients. Again, I want to pause for just a minute and see if there are any questions about policy gradient algorithms at this stage. Thanks. Yes. That's a fantastic question. So the question is, in the policy gradient algorithm, the approach was only updated at the end of each episode. And are there any approaches that would allow updating after every step? That's actually the perfect segue to the next part of the lecture, where we're going to look at temporal difference learning methods that do exactly that. The limitation of updating at the end of episode is that if an episode, for example, is very long, you have to wait for a very, very long time before you can actually learn from experience. So that can be data inefficient. And that is one of the kind of limitations of policy gradient methods, which these other types of approaches look to address. Good question. Let's see. Again, it's hard for me to see arms, so if you have a question, just shout out. Oops, sorry. It's sorry. Say again. It's hard to. Yes. So the question is whether the action of the agent actually influences the state. Yes, the action is typically assumed to influence the state. So one kind of example to visualize that could be if you're navigating some unknown environment. Every time you take a step, you end up in a different state. So in that sense, there is this feedback mechanism. Yeah. Yeah. Oh, smart. There's a microphone. Good job.
The question is about the reward function. And sometimes it might be really tricky to specify your reward function. So are there any cheap, non-expensive ways to assess your reward function other than inverse reinforcement learning?
Very good question. So you're familiar with some work in reinforcement learning?
Robotics with infinitely immense state space. We have some problems there.
Right. So as you mentioned, defining a reward function is very, very hard. And sometimes it's very difficult to find experts that understand the problem well enough to specify the reward structure or reward function that would be effective for learning the task. Now, one solution that you mentioned is actually a very good and very popular one, inverse reinforcement learning, where an agent learns from observing the behavior of another agent. In inverse reinforcement learning particularly, an agent would observe, for example, a human demonstrating the task. This is something that is done, for example, in robot manipulation. So a human might remote control a robot to do a task, which allows the experimenter to collect the experience necessary to then learn from. Given that experience, the agent would first learn or would try to infer the reward function that the demonstrator may have had in mind or may have been following when generating that experience. And then as a second step, the agent would learn to actually optimize its behavior for that inferred reward structure, for that inferred reward function. The more general question of whether there are cheap ways to get rewards, I think it's a very hard one. One direction that was mentioned by a student earlier was the direction of curiosity, novelty. So those are kind of ways or attempts to very generally come up with reward structure that may work very well in a very wide range of settings, so that you can come up with reward structure once and then apply it over and over again to learn very different tasks. So I think that is an interesting kind of direction, and it might be one that works particularly well when combined with, for example, very sparse rewards. It's still a wide open area. So at ICML this year, there was a workshop on goals in reinforcement learning, kind of trying to understand where reinforcement learning agent goals and reward structure should come from. There's some really interesting ideas along the lines that were mentioned, but it's still an open area. And if people have cool new insights here, I'd love to hear some of that or see the research that comes out of it. Yeah? Oh, fantastic question. So the question is, in RL, do actions have to stay constant or can they change over time? And the answer is they do not have to stay constant. So in many settings, it's assumed for simplicity, but there are actually very natural kinds of problems where the set of actions can change, for example, at every step. One example are the text worlds that I mentioned earlier. There you might have different verbs or kind of words to refer to the current objects in the environment, and as they change, that can change the action space that you have available. Very good question. It's again, dealing with these very complex action spaces is still a bit of an open problem, but it's definitely possible to do that. Yeah. I see a tentative arm raise there. Yeah. So if I heard you correctly, you're asking whether there are problems where you don't really have enough information to formalize the state space. Is that right? Mm-hmm. Mm-hmm. Right. So there are problems where the Markov assumption is not assumed to, or where we are not assumed to observe the full information of the state, so everything that is relevant for addressing the problem at each time step. And there is a formalization called partially observable Markov decision processes, which is more general than Markov decision processes, which covers those kinds of settings. So those are settings where the agent's actions in principle may have to depend on anything that occurred in the past, so any part of the history. And there are key challenges around how to effectively, systematically learn in those settings. So learn representations or kind of abstractions that allow the agent to take decisions given its uncertainty over what state it might be currently in. So that is one kind of direction that I could imagine. The other one is, if you don't know what needs to be put in the state, then the state representation might be over complete. So for example, it could be something where you throw in all the information you have and then use a powerful model and hope that you have enough data to actually extract all the bits, all the features that are actually relevant for the task. So that might be another way to approach it. That might make learning challenging because as the state space grows and as the complexity grows, you need a lot more data to actually learn the task. So if you have expert knowledge or some prior information about what should be in that representation, that will make learning more data efficient. Let's see. Thanks. Mm-hmm. Mm-hmm. Mm. That's, again, really good questions. So the question is, in relation to POMDPs, or maybe as an alternative, you've seen work where people use RNNs or other recurrent models to kind of learn abstractions over the history of interaction. To me, so using these kinds of recurrent models is one type of approach that can work well in a POMDP. And some of the work by Matthew Hausknecht, for example, showed that in, for example, Atari games where some information was redacted out, so for example, where the agent could only observe every other frame, LSTMs or other recurrent models were very effective at capturing that information. At the same time, it's a very active research area, so there are people looking at learning representations that more accurately reflect the uncertainty over potential future trajectories. There was, for example, work at ICML by Max Eagle, where they used a mix of a model-based approach and a model-free approach, where they had one predictive model, so a generative model that would try to predict the possible ways in which the future could roll out, and then they would couple that with a reinforcement learning approach that would then base its decisions based on that understanding of how the future may evolve. So they're very kind of interesting types of approaches that can model representation learning in POMDP settings. It's again still quite an open research field, so there are some interesting ideas, and maybe have some interesting ideas on how to address the problem as well. All right, I might be missing some arms, but let's move on to the next section. So one of the first questions there already nicely kind of provided a segue to the final part of the talk, where I want to talk about temporal difference learning, or Q learning. One key motivation here is that, as was already mentioned, in policy gradient approaches, the approaches are quite data inefficient. We may need to wait all the way until the end of an episode to actually correctly estimate the current state distribution from samples to get enough data to actually update our policy reliably. And something that I haven't really mentioned as much, but that is also a problem, is that these types of approaches actually have very high variance. So you may not need a single episode, you may need many, many episodes to actually effectively estimate or accurately estimate your gradient and to compute the next direction in which you should update the policy. Now, an approach that looks at alleviating this problem is one called temporal difference learning. Here, instead of focusing on improving the policy, the algorithm focuses on learning the value of a policy. So intuitively, it tries to estimate how good an action is given the current situation that the agent is in. And the key insight that we'll be building up to is the insight that these value estimates can be bootstrapped from previous estimates. And this is actually a very cool insight that came originally from early work in optimal control. It was developed initially by Richard Bellman in the 1950s. And it's a type of insight that is still underlying a lot of the current work in reinforcement learning. So it's a fascinating set of approaches. In this part of the talk, we'll be using a running example which builds up to temporal difference learning in Malmo. So I very briefly mentioned Project Malmo already. It's an experimentation platform for AI that my team built and released on GitHub. It's freely available, and some of the examples that I'll be mentioning are part of the GitHub repository. So you can actually go install this and try this out at home. So the running example that we'll be using is an adapted version of the cliff walking task, which is also a task that is one that is used in the Sutton and Bartow book in chapter 6, if you want to look it up. So in this particular task, we see an agent here in third-person perspective, which always starts at the starting state over here. It can move north, east, south, and west, and the task is to learn to navigate to this blue goal in the end. Now, of course, being a reinforcement learning agent, this agent initially doesn't know anything about the world. It doesn't know all the things that we can see here. It doesn't know that it's surrounded by lava. It doesn't know where the safe kind of places are to walk. And it doesn't even know that there's a goal and that there's a blue block at the end that it can reach to get a high reward. So all of those things it has to learn from interacting with the environment. So if we start by initializing this agent with a uniform random policy and just run it on this task, this is what happens. It walks around randomly for a bit, and then it dies in lava. Very sad. All right. Now, how can we do better? To look briefly at how this problem is represented, we can look at the states, actions, and rewards that are used in this particular example. In the example here, we assume that states are represented in this tabular form. So you can see here this white spot where the agent is currently located. We can see each square represented by an entry in the table, here shown as a little square. And in each square, we actually see these 4 dots, which illustrate the current value estimates that the agent has learned so far. So for example, when it's in this particular square here, the agent estimates that going south is negative, indicated in red, and it thinks that going north, east, or west is not too bad, maybe fairly good, indicated in this lightly green color. So this is the kind of representation that the agent has and that it learns in. And over time, the agent updates these estimates so that they more and more accurately reflect the consequences of the actions that it can take in this environment. In this particular environment, the reward structure is such that the agent gets a small negative reward, minus 0.1, whenever it takes a step. It gets a very strong negative reward, let's say minus 1, whenever it falls in the lava, and it gets a very positive reward, plus 1, when it reaches the goal. And episodes are reset whenever the agent falls in lava, or when it reaches the goal, or after 100 steps. So that's the structure of the problem here. We've seen the agent fall in the lava. So now the question is, when we look at a basic policy gradient algorithm, for example, reinforce, as we developed earlier, we'll require many, many policy rollouts to estimate returns. And what's hard here is that if we assume a random walk on this cliff, it will actually take a lot of random steps, a lot of random rollouts, until we find this policy randomly that actually gets the agent to the goal so that it can learn from the positive outcome of that episode. So it's very hard, very data inefficient to learn this using policy gradient. The question is, can we do better? And of course we can. And the ideas underlying this come from this area of dynamic programming that I mentioned earlier. Is it time to go? I think we have about 15 minutes, so let's see if we can give you a good idea of how we can learn in this particular setting in this time. So the first kind of concept that we need to introduce here is the notion of a Q function, also called an action value function or a state action value function. And what this function captures is the value, the expected value that we can get when we start from state st and take an action st, and then follow the current policy pi from then 1 onwards to infinity. So another way to write this is under this expectation under our current policy pi. We want to look at this discounted sum of rewards when we start from state st and take initial action at. And again, it's the discounted sum of rewards which goes from our current time step up to infinity. So this quantity is what we call the Q function. It's the action value of state st and action at under our current policy. Now, the key insight, and here it comes, is that we can take apart this particular quantity. So we can just chop off the first element. We separately take the reward that we actually got in the next time step, and we write that out as RT plus 1. And then the remaining quantity is, again, an infinite sum over discounted cumulative rewards. So we can write this like this. And now if you look carefully, we realize that this quantity here, e pi gt plus 1 given st plus 1 and at plus 1, is exactly the same as this q value, just one step in the future. There we go. And this is the key insight under dynamic programming, that we can solve a problem or look at solutions for a problem by breaking it down into subproblems, in particular along this recursive structure. So we can form different estimates along different points in time, and we can, what is called, bootstrap from our earlier estimate. So for example, if we don't have a current good estimate of Q, but we have an estimate, of QST80, but we have a reasonable estimate of Q at the next state and the next action, then we can improve our estimate of QST80 given this quantity by just discounting and adding the reward that we observed by interacting from the environment. So now, if we had Q value estimates that converged, then these two quantities would actually be the same. So if we had learned those correct estimates, then our estimate of the value of taking action AT and ST would be exactly the expected expectation of the reward that we observed plus the discounted Q value at the next state. And we can use this to optimize, to update our estimates accordingly. Now this quantity here, this difference, is what is called the temporal difference error. And all that Q-learning does is it tries to minimize the temporal difference error as it goes and collects interactions with the environment. I won't have time to go into much more detail on this, but I just want you to kind of reflect on this notion that we can break down this infinite sum of returns, and that this allows us to formulate the problem of estimating the value of the current state in terms of our estimate of the value of the next state. And it's a very fundamental notion to grasp, and if you understand this, then understanding algorithms for Q-learning, for example, will come very naturally. So here is a summary of the actual Q-learning algorithm, and I just want to point out the parts where this temporal difference error plays an important role. Right? So as before, we interact with an environment in this interactive fashion that we saw before. We choose actions A from our policy, and S we observe from the environment. There's a small detail here in that the policy that we follow at this stage is usually one that allows for some exploration. One popular choice there is epsilon greedy, where some epsilon % of the time you take random actions to ensure that you'll not converge too quickly to a suboptimal policy. Now, given the data that we interactively collected, we can then update the Q values. And this is the key part here. We look at our current Q estimate, and this is assigned its new value, where the new value comes from the current estimate, plus some learning rate alpha, which is again a hyperparameter, times the temporal difference error. Right? So that's the key notion there. To make that a little bit more visual here, imagine that our agent just took a step to the right. Now we find ourselves in this new state, and we can update the value of this particular action in this particular state using our estimate of the value of this next state. And if we run this algorithm for about 10 minutes, we arrive at this policy. Let's see. Wait. So as you can see over here, as the agent explored the environment, it's learned all the state action values for all the states that it encounters as it goes through this environment. And you can see the ones that are in more green over here indicated in green. And the red ones are all the ones where it falls into lava, so it has a very negative estimate of that value of the state. Very, very quickly, as we're wrapping up, there's a really nice connection to Q-learning with function approximation. And again, the temporal difference error is the very fundamental concept that underlies Q-learning with function approximation. So as we switch from reinforcement learning with this tabular representation I showed you to one that uses deep neural networks as function approximators, the key insight is that we can still use this temporal difference error, and you'll remember that it has exactly this form as we saw in the tabular case, and we can formalize that as an objective function, which can then be minimized using gradient descent. So there again, we have the connection to deep learning, to using something that can be implemented using your favorite deep learning toolkit and optimized very efficiently using all the insights that have been gained in supervised deep learning, for example. Now, very quickly, I want to look back at, as we discussed earlier, one of the key kind of demonstrations of the power of this kind of approach was in this work on playing Atari games. Here, the key result was that a single RL algorithm can learn to play 49 different games from pixel images. In addition to kind of demonstrating how powerful deep Q-learning could be, there were also important insights about the role of stabilizing training. And if you're interested in those and haven't read this article yet, I recommend it because there's really nice insights about stabilizing training using what's called replay memory and a separate target network that allows more stable updates during learning. We can take exactly the same algorithm and apply it to different settings. So for example, here, I took another Minecraft navigation task, implemented DQN exactly as it was used for playing Atari games. And in the visualization here, you see on this side the state observation that the agent gets. So it gets just the 4 most recent pixel images that it sees from the first-person perspective. And next to it here, you see its estimates of the value of each action. So it's the state action values that we can learn using temporal difference learning. And again, applying exactly that same algorithm, we arrive at an agent that is able to very smartly navigate to the goal without ever falling in lava. And that is after about 1 million training steps, so there's still some data efficiency issues to address there. A little bit of further reading, and I want to leave just 5 minutes to discuss some current challenges in the area. Further reading, if you're interested in this, again, the Sutton and Bartow book has a wealth of information related to temporal difference learning, especially Chapter 6 and Chapter 9 to 11 are very relevant. So Chapter 6 introduces those ideas for the tabular case, 9 to 11 for the case with function approximation. There are 2 kind of really interesting applications of reinforcement learning that I also want to call out. The first one is work that was done at Stanford about 10 years ago, and for a long time it was a very kind of canonical, popular application of reinforcement learning, and that is using reinforcement learning for aerobatic helicopter flight. If you haven't seen the website or the video, it's very cool. They use a mix of reinforcement learning techniques, so they use a lot of informed modeling choices to model the dynamics of the environment. But then they use this as a starting point to learn very complex kinds of maneuvers using this helicopter, which is really cool to see. Another application that I want to highlight is one that spans, or kind of that makes this step from reinforcement learning to applications in both a health setting and a human-computer interaction setting. And this is a study that was done in collaboration between reinforcement learning experts and experts in this particular health area. What the authors looked at was the problem of adapting prosthesis to the wearer of the particular prosthesis. In this one, it was a prosthetic arm. And the authors were looking to understand how adaptive machine learning or reinforcement learning could be used to tune the configuration of such a prosthetic arm to the specific requirements of the wearer. And they were able to find that by using adaptive learning, by using the kind of predictive modeling that reinforcement learning allows us to do, the wearer of the prosthetic arm was able to much more quickly control the prosthetic arm than they were using existing current methods. So it's a really interesting kind of case study of what kinds of applications can be enabled by reinforcement learning. It's very exciting. Right. So as I mentioned in the last few minutes, I want to just point out a few kind of key challenges, both in terms of applications and in terms of research. On the application side, I mentioned earlier that reinforcement learning is such an exciting research area, is such an exciting area of machine learning because it's so general, because it can span applications from optimal control all the way to trying to understand, trying to model what might be happening in the brain on a neurobiological level. So in this sense, the application areas are really, really broad, but we're not seeing reinforcement learning applications in a huge wide range of kind of real-world applications. And I'm always wondering kind of what's necessary, what are the next steps that are going to enable those kinds of applications. Three factors I think are really important here, and those are education tools and infrastructure. As many of you are aware, on the education side, reinforcement learning is still much less widely understood than other parts of machine learning, for example, supervised learning. So events like this one can actually do a lot to educate people, to get people thinking about how to formulate problems as a reinforcement learning, and maybe how to address those problems using existing or new kinds of insights in how to effectively learn in complex, interactive, and noisy environments. There's also this set of tools, and tools in education, I think, go hand in hand. If people have a theoretical understanding of these types of approaches, but can't really play with them directly, that will inhibit the kind of speed of innovation in those areas. And on this front, on the kinds of tools fronts, I'm really, really happy to see that there are more and more tools that people can use to experiment with reinforcement learning in a huge variety of settings. These are just a few that I wanted to call out. I've mentioned Project Malmo, but there's a wide range of environments, often game or simulation environments, that are now available online for free, often on GitHub. Those include OpenAI Gym, which has a really nice wrapper around the Atari games, as well as a wide range of other kind of environments. There's DeepMind Lab, which has complex 3D tasks in 3D environments. There's Unity ML Agents, which uses this game development platform Unity to allow people to experiment with different kinds of tasks, different kinds of environments that can be addressed using reinforcement learning. And it also includes reference implementations or baselines of some state-of-the-art reinforcement learning algorithms. Similar reference implementations are available here under the Dopamine project. There's a very scalable implementation under Ray RLlib, as well as the OpenAI RL baselines, which are really popular, again, in research and education, and just trying things out and tinkering with these types of approaches. So I encourage you, if you haven't, to go and try and explore some of those resources and try out reinforcement learning in your course of study or at home, and learn about what it means to address problems from a reinforcement learning perspective. There's also reinforcement learning competitions on CrowdAI, which is a competition platform similar to Kaggle, but focusing on reinforcement learning. On infrastructure, I mentioned there's one type of reinforcement learning problem, so-called contextual bandits, which are already routinely addressed in industrial settings. So these are particularly relevant for recommender systems, optimizing search results, and the Microsoft's custom decision service is one of the offerings that's available there. I'm out of time, so just a very quick overview of some key research challenges in case you are working in reinforcement learning. I'd love to hear some of your ideas there. One key challenge is that of exploration. How do you know what parts of the state space to explore? Challenge of representation learning. Now that we're using more and more general observations, just pixel images, how can we encourage reinforcement learning agents to learn the right biases that allow them to learn quickly? problems in multitask reinforcement learning. How can we get agents that don't just learn to solve one individual task, but that can transfer knowledge to a huge variety of different tasks that may be related in some specific ways? And finally, how can we develop multi-agent reinforcement learning approaches that act not in isolation, but in collaboration, for example, with other agents or even with human collaborators? Finally, if you are working in reinforcement learning and are interested in exploring some of the challenges around multitask and multi-agent reinforcement learning, we are collaborating with CrowdAI and Queen Mary University to organize the Marlowe Challenge, which will take place on top of the Malmo platform. It's opening for submissions next week, so check it out. Thank you so much for your attention.